Hello, my name is Jordan Marcincavage, EDM Applications Engineering Team Leader here at Makino Mason. Today we're going to talk about the EDBV8 fast hole EDM drilling machine. This machine is primarily used to machine film cooling features in large aerospace and power generation turbine engine components. After the presentation, we'll open it up for a Q&A. If you happen to have any questions during the presentation, feel free to use the chat box. For the EDBV product line, we have two sizes of machines. The EDBV3, which is used for primarily small parts, and then the EDBV8 that we're talking about today, which is primarily focused on large parts from the power generation industry. Today we're going to discuss the aerospace industry's current and growing manufacturing needs, aerospace components and requirements for EDM drilling, Makino's large turbine engine component EDM drilling solution, the EDBV8, the structure and capabilities of the machine, as well as popular option content. With turbine engine manufacturers focusing on improved engine performance and fuel efficiency, new component designs require the use of more complex film cooling features designed than ever before. And these features have more varying shapes and vectors. So what's important about this is with the addition of more vectors, it makes it more difficult to machine the features with older style technology like sinker EDM and comb electrodes, where you're trying to group like features at the same vector. So it's important that you have a machine like the EDBV8 that uses single point tooling. So single point tooling is basically the use of a single tool that has a single machining point, similar to an end mill. So with more holes, you have the need for higher process efficiency, which includes less setups, less scrap, and faster cycle times. Individual turbine or turbofan engine components are typically referred to as blade or vane details. The blade and vane components are commonly cast details that contain inner hollow features for cooling and weight-saving purposes. And EDM drilling is used to create film cooling features in the blade and vane sections. So by blade, we're talking about on the left side of the screen, we can see a blade and with the top cross section, so you can see some of those internal cavities. Same for on the right side. This is an example of a doublet vane. Also, once again, cross section, so you can see the internal cavities. And whenever we talk about film cooling features, we're talking about some of these features on the airfoil, some of the diffusers and holes shown on this airfoil, and then on the doublet airfoil as well. One of the biggest quality concerns with machining of aero engine components are backstrikes. So what backstrikes are is drilling through one wall and then making contact with the opposing wall. So if you do backstrike, it can disrupt airflow and the cooling efficiency of the component. And the part integrity is also compromised. And it's also a possibility that the part will just become scrap. Cooling holes can be simple round holes or special shaped holes called diffusers. Diffuser shapes vary and can be tapered cones or rectangles or another shape that basically blend down into a final through hole. The diffusers are produced to modify or control the airflow and the cooling of the component. So basically what happens is air comes in through the back side of the part and exits through these film cooling features. So the diffuser, its main purpose is to effectively direct air across the part. For the EDBV8 general specifications, we have an X and Y stroke of 800 millimeters by 600 millimeters, Z-axis stroke of 500 millimeters with an option for 750. And the Z-axis is where we hold the electrode. W-axis stroke, which is where we hold our positioning guide, that's 500 millimeters as well with the optional 750. Each machine comes with a MMK tilt rotary table. So by standard, it's a 50 kg, but there is actually a popular option of 150 kg as well. For that tilt rotary table, we have an A-axis, which is full rotation, 0 to 360. And a B-axis tilt of plus 30 to minus 110 degrees. The MMK table also has the availability for an Aero or 3R chuck. For the electrode diameter ranges on this machine, we're going from 0.2 millimeters up to 3 millimeters with an option for 6 millimeter as well. Max electrode length of 450 millimeters by standard with an option for 600 millimeters. And we're going to cover some of this additional option content later in the presentation. For the C-axis rotation or the spindle, we're rotating up to 1,000 RPMs. So anytime that we're machining, we're always rotating the electrode. And this really helps with getting even electrode wear and also helps with concentricity of the hole. For through spindle flushing pressure, we can go up to 10 MPa. And this really helps with debris evacuation and machining speed. Also, the machine has a programmable 3-sided rise and fall work tank, which helps us or enables us to do submerged machining. 24-station ATC, and for this machine, we're using deionized water for the dielectric fluid, and this really helps us get the fast machining speeds. The machine also has an onboard filtration and DI resin system that are digitally integrated and monitored by the Hyper-I control. So if you look over on the left side of the screen, you can see the conductivity is currently running around 15 microsiemens. And as we start machining and adding debris into the water, the conductivity is going to rise. And once the conductivity crosses a certain threshold, water will automatically start to circulate through the DI to the resin tanks and lower the conductivity. So we're also always monitoring the filter back pressure as well. So as you can see also on the left side, as long as our filters are running in the green, everything's okay. Once we get up into the yellow, we'll post an alarm on the Hyper-I screen to give the operator notification that they'll need to change the filters soon. And then once they get into the red, we'll throw an alarm and basically force the operator to swap out the filters. The machine also has a standard chiller unit, which synchronizes and maintains the water temperature to the machine cast structure. So what this means, if we take a look at the slide, we use the casting actually as a holding tank for the water. And since the water is always flowing through the chiller, which follows the ambient temperature of the facility, it really helps control or minimize the effective temperature fluctuation, which can affect machining accuracies. The machine also utilizes a rise-fall work tank, which allows for fully submerged machining operations across multiple workpiece sizes. This still allows open access to the work zone for easy load and unload of the workpiece, as well as automation possibilities. The operator can still easily view and monitor the machining process, and the tank position is automatically commanded and controlled through our conversational programming method model plan. The benefits of submerged machining are increased machining speeds, improved chip and debris evacuation, more stable and consistent machining, improved feature quality and surface integrity, improved breakthrough detection, and also eliminates the need for manual adjustment of auxiliary flushing. So as you can see from the picture at the bottom of the slide, we have non-submerged versus submerged machining. And it's easy to see that the submerged machining has a better surface finish and quality, and this will lead to a more efficient airflow. Machine also utilizes a 24-station ATC, and you could either load this up with various sizes of tooling or redundant tooling to help reduce the amount of operator intervention. But if operator intervention is required, you are able to replenish tooling without interrupting the machining process. For tooling, the machine uses an integrated electrode holder and die guide assembly. So what this means is the electrode holder and the guide holder, they assemble to make one unit that is loaded into the ATC magazine. And whenever you perform the ATC, the electrode holder and guide holder are automatically separated. And this basically leads to a very reliable and efficient tool change. A vibration control finger is used to reduce the whipping and bending of small diameter electrodes. Since we can use small diameter electrodes and we rotate the electrode up to 1,000 RPMs, it's important to have some way to keep the electrode vibration and whipping or run out to a minimum to help stabilize the machining process. The finger advance and retract are also automatically controlled through model plan. So as you can see in the picture, with a full-length electrode, the single vibration control finger is deployed, and as the electrode is depleted or becomes shorter, the finger automatically retracts to make room for the Z-axis. One of the biggest quality concerns with the machining of film cooling features and airfoils of aero engine components are backstrikes. So to help avoid backstrikes, we use a high-frequency adaptive discharge monitoring during our breakthrough detection. Our breakthrough detection is reliably detected within 1 second or 1 millimeter of depth at optimum machining speeds. We also have various types of breakthrough detection technologies to accommodate different types of machining situations, mainly on the exit condition. If you're exiting normal to the surface or on a high angle or maybe on a radius. We also have programmable thresholds to optimize the settings on a per feature basis. It's also possible to add a Renishaw RMP 400 probe to the machine. And we use this with our 6-point probing, which measures part alignment error using the part's 6-point datum structure. So when we talk about the 6-point datum structure, basically talking about primary, secondary, and tertiary points. So with the 6-point probing, we're utilizing vector probing, which means we have the ability to move the probe along a combination of X, Y, and Z axes. So we don't have to move primarily in X or Y or Z. We can move in any combination of the three. And this is an iterative process, which means that the measuring routine is repeated until the specified correlation tolerance is met. Ball probing and shank probing are both available. So for ball probing, we're talking about making contact with the workpiece with the sphere or the ball at the end of the probe. But it is possible to also use the shank or a point on the OD of the shank to probe as well. And where this is a benefit is if you have a point that falls on a small radius, like on the leading edge of an airfoil, it may be better to use the shank type than the ball. The linear and angular error found during the measuring is then used to compensate the nominal machining locations. So as we said before, the 6-point probing can locate the part and determine the part's actual location and orientation. So in the picture here, we have the green model, which is basically model space. There is no part error. The part is in the exact orientation and location as programmed. And then we have the red model. This is actually where 6-point probing determined the actual part to be. So now we need to compensate the machining locations to match the red part. So after probing, we'll populate the data for the work installation offset that's used in this 6-axis compensation calculation. And when we talk about this information or this data, talking about the information at the bottom here. So this is the X, Y, and Z linear errors of the part and the X, Y, and Z angular errors of the part. So this would be the errors about, the angular error about the X-axis, Y-axis, and Z-axis. So with this, we have a total of 32 storage registers that are available for parts with multiple datum structures, such as vane segments with multiple airfoils. The use of 6-point probing along with the compensation allows for simple, cost-effective fixturing. So basically, you can hold the part in any way that you want to where you have the access to most machining features. You don't have to locate on the 6-point datum structure itself because we're going to come in and probe it. This machine also uses the Hyper-I control, which is a universal graphical machine interface that's used on all newer EDM platforms. Has a 24-inch touchscreen, onboard digital manuals, and training system. We also use HyperConnect for interconnectivity and monitoring. So what this does, it allows you to view the Hyper-I from your PC or another device. We also use conversational model plan programming with project screens that organize and minimize operator inputs. Model plan is a conversational programming method that allows the user to create a program by entering key items like tooling, feature, and location information in the tabular format. It's basically just a way to create a program on the machine. So the program can be created on the machine at the Hyper-I control, or it can be created offline through CAM with the use of a custom post-processor to output in just basically the model plan format. Machine functions such as automatic electrode changes, electrode length tracking, and work tank positioning are automatically controlled by model plan, which really helps you have to interact or program less features of the machine. For diffuser processing, the use of single-point tooling allows for CAM-generated toolpaths for just about any diffuser geometry. And on the screen, you can see a couple different examples of this diffuser geometry. And And also the toolpath you can see is very similar to just a milling style toolpath. So as we're machining, the electrode is always eroding away. So the electrode is always getting shorter, which means our toolpath actually needs to feed down in a helical or a ramping motion. And with model plan, we have the ability to just tell model plan the anticipated electro wear rate, and it'll actually make the ramp for us. So we can just post out the code in a standard planar XY motion with basic Z step downs, and model plan will take care of the ramp for us. So what makes this nice is you can easily adjust the diffuser angles and depth by just changing this one model plan element without the need to repost the entire diffuser toolpath again. So now we're going to discuss some of the popular option content for the EDBV8. So on the left, you can see a standard EDBV8 machine, and then on the right is a heavily optioned machine that we call the riser EDBV8. For some of the popular option content for the EDBV8, we have the 750 millimeter extended Z and W stroke, and that allows us to use longer electrodes. And then we take that entire column that holds the Z and W stroke, we put that up on top of a riser. And that allows you to load a larger workpiece into the machining area. We also have the ability to, or the availability for the 150 kg tilt rotary table. That is also on a riser. As we said before, longer electrodes, so 600 millimeter electrodes, and additional vibration control fingers. For the tilt rotary tables that are available for this machine, and just to kind of put them into perspective, on the left side, we have the standard 50 kg table that comes on the standard machine. And then in the middle, we have the 150 kg table that is also a popular option for the standard size machine. And then on the right, we have the 150 kg table on a riser that we use in the EDBV8 riser machine. And the benefit of this table is we have the ability to tilt larger parts over without making contact with the casting or other table components. Another option that's available is the additional vibration control fingers. So you can see on the left side, we have a picture of the standard setup for the standard EDBV. So as we said before, you can use a 450 millimeter electrode by standard. So that's a 470 millimeter gauge length once you add on the electrode holder. And since the electrode is on the shorter side, we only use one vibration control finger. For the riser EDBV8, since we can use 600 millimeter electrodes, which gives you about a 620 millimeter overall gauge length, we need the additional vibration control fingers to help to control the run out vibration of the electrode to ensure that we get nice stable machining. Now we'll go to Jake for a machine walk around out on the showroom floor.
Thanks, Jordan. I'm going to give everyone a quick overview of the EDBV8. This is our showroom machine. It's an EDBV8 that has a 150 kg MMK table. This table is also on the risers. This allows us to rotate the V axis past 90 degrees. Also, this comes with the column riser for the Z and W axis. This allows us to take an electrode that is up to 600 millimeters. And it is also equipped with a hyper eye, just like the rest of our Makino EDM machines that are newer. And we are going to give you a little demo of the machine. All right, so first we're going to execute a tool change. So as you can see, this has the one assembly, so it's the electrode holder and the guide in one piece. And then the W axis is going to come up, and this is what's going to separate the guide and the electrode. So on the riser machine, we have 3 additional stabilizer fingers, and this is what helps keep the electrode stable, and it helps with concentricity and stability in the machining process. So we also have the rise fall work tank. We're going to demonstrate the tank going to the max height. And this allows us to completely submerge taller parts if necessary. Good. Now this tank door, it'll track with our machining position so that you're not always all the way up or all the way down, and this will keep the machining process completely submerged. So next we'll demonstrate some of the movements of the machine. So here we're moving to the X positive side of the stroke. Now most of the machining is going to take place on the X minus side here. Because we have the table shifted on the X positive side, we're able to tilt our part B minus, and this allows us again to get those taller parts tilted, and then we can rotate A and access all the different vectors that may be necessary. All right, so here's our A and B axis moving simultaneously to help speed up those positioning moves. And again, we're able to go past 90 degrees because of the riser underneath the table. And because the table is shifted to the X positive side, we don't have that complete positive V stroke, but we can go a little bit on the positive side. Here's our through spindle flushing, the spindle on. Notice with the stabilizer fingers, we don't have any of that wobble. And again, that'll help stabilize the machining process. And yeah, that concludes the demo. So now it's going to put the tool away. But what I'm going to do is I'm going to stop this program. And I want to run this over again, and I want you to notice that even though a program is executing right now, I'm still able to open the ATC, and I can pull out a tool. And let's say that this electrode has been spent. I can replenish the electrode. I can place it back into the ATC, close the door, all while the program is still running without any interruption to the process. Now that we're at the back of the machine, we're going to talk a little bit about some maintenance items back here. So here we have a holding tank. Now notice that this protrudes from outside under the casting. The reason for this is because we have a riser machine, we require more water to fill the tank that can come up to that max stroke if we need. So then we'll go over here. Here is where our filters are stored. You can easily change these by lifting up this cover and remove the filters and replace as needed. We have our DI bottle, and this can be moved into a different position, whatever suits your shop floor. And we also have our chiller here. So again, with our chiller, this helps regulate the temperature because our water is stored in the casting. And what this does is follows the ambient temperature of your shop, and this helps reduce any inaccuracies that could be caused by temperature change. And here we have our generator cabinet, and just to the left there is our transformer cabinet in case any maintenance is needed or repairs. And then right underneath here we have these access panels, and inside of here we have pumps and many other maintenance items that you can easily access. And with that, that concludes the walk around, and we're going to send you back to Jordan.
So in conclusion, just to review a couple of things that we talked about. So the EDBV8 is a purpose-built machine for large aero engine components. We have the use of single point tooling that allows us to accommodate the multiple vectors and diffuser shapes for new part designs. Submerged machining, which helps improve machining speeds and quality of features. The breakthrough detection that helps us avoid backstriking. On-machine probing paired with the compensation that eliminates the need for fixturing on the 6-point datum structure, and also the popular option content for the EDBV8. So now we'll open it up for live Q&A to answer any questions that you may have.
All right, thank you, Jordan and Jacob, for that great presentation. So now Jordan and Jake are available for any questions that you might have. If you look on the right-hand side of your window there, you can see there's a Q&A and a chat. You can put in any questions you have there. Jordan, there's one in there right now. Alejandro is asking how you avoid flexion in deep drilling applications. So do you want to touch on that in terms of your drilling depths and how you handle deeper?
Sure. So I'll take that one. So how do we avoid flexation and deep drilling applications? So a lot of that is handled with having, a stable condition in our drilling. So our generator works to maintain a consistent spark gap. And inside of the EDM process, the electrode actually never contacts the workpiece. So we don't have to worry about, the electrode getting deflected and running out.
Okay. And to follow that up, what kind of L to Ds were you talking about being able to accomplish on this machine?
I would say our limitation would be to, our electrode length and then our wear. As long as we have a good W axis alignment, which is something that we check, the limitation would be on the length of your electrode and the wear. So, if we're running, say, like a 0.2 millimeter electrode at, let's say, 200 to 300% wear,
Okay.
you're looking 6-7 inches or so.
All right.
All right. So next, what electrode diameters are used on this machine? So go from 0.2 millimeter up to 3 millimeter by standard. Then we also have an option to go up to as big as 6 millimeters as well, if needed.
Okay.
All right.
I got a question on that, Jordan. So when you go to 6 millimeters, is there anything additional that you need to add to the machine?
So the option content includes a additional booster for the generator, so which takes you from 30 amps to 60 amps. There's also some differences in the electrode holders and guide plate assemblies as well, just to handle the increased diameter. But outside of that, those are the two main options.
Okay, so you need the booster because of the bigger electrode size diameter, right?
Yep.
Okay,
Yep.
Very good.
All right. And can you run multiple parts in one setup?
Yep, I'll take that one. So, yes, you could. So if you had a fixture that could, handle multiple parts, we have multiple work offsets and also compensation registers if you were to use, probing on those parts. So as long as you are not, blocking the vector to access that feature, you can run, in theory, up to 32 parts.
All right, very good. We got another question here, guys. What is the expected hole size repeatability from hole to hole?
So on this machine, since it's a water-based machine, our target is primarily speed. But on a hole-to-hole basis, you can normally expect around 1 thou, sometimes 2 thou, depending on how aggressive and fast you're trying to go.
Okay. Very good. This good question here. Is this program with any CAM software, or would it be specific programming software for this machine? So in other words, is it any general CAM software you can use, or do you guys use something specific?
Yeah, so in our group, primarily we use Siemens NX just because of having the aerospace focus. But pretty much you'd be able to use probably any 5-axis software that has 3+2 programming capabilities. The only real requirement would be you would have to have the post processor output the model plan format.
Okay. All righty. Another one here, Christopher. Have you ever been able to program you've been able to program and machine small, narrow slots, similar to how the diffuser is machined. So, can you just program a slot as opposed to a diffuser shape?
Theoretically, it can be done. It's not something that we'd normally target with the machine, but in theory, you could create a slot or a shape in the same methodology.
Okay.
You would just probably have some challenges on sidewall straightness, bottom radius, things like that.
Okay. All right. And the slot width would, of course, be dependent on the electrode size that you're using, right? The diameter.
Yeah, correct.
Yep. And so leading into that, another question that we have here is what kind of overburn is normal with this machine? So
Yeah,
yeah, go ahead.
for that one, it's dependent on your electrode size, but I would say the range, a smaller electrode would be about 2 thou overall, and then a larger diameter, you're pushing more current, probably be looking 4 to 6 thou even.
Okay. And that's total overburn, right?
Total, yep.
Yep. Okay. See, following up on the slot question, Chris was thinking of through slots is what he was thinking of. So there wouldn't be any problem with the bottom?
That is correct. So it'd all just be about then being able to control the tip of the electrode depending on how far you needed to go down past the bottom. And then some of the same canned statements on wall straightness, and that type of information, that type of stuff.
Yeah, and I would think depending on the particular part, if there was nothing behind the slot, you could feed through further to straighten out the walls, right?
Yeah, you could. And then you just have to consider then on if you reuse that electrode, that extra, because it's a brass electrode, so you may incur like additional wear in that area where that previously used electrode you could need to dress it off possibly.
Okay. All right, great. All right, well, I don't see any more questions. So I want to thank everyone for taking time today and joining us on this presentation on the EDBV. Thank you guys. Great presentation. And if anyone has any questions, reach out to your Makino rep, and Jordan and Jacob can answer anything that you need.
Thanks.
Thank you.